Okay, so let's go over first of all the formula sheet, right? You're gonna have tables like this. I mean, I'm gonna use this table from our book, but you can find probably tables like this in many books or even on the internet in general if you look for it, like a table of quadrics or something of the sort. So, and this is again for my students because other professors may require memorization for these equations, but I don't find it practical. Just make sure you know how to use this table correctly. So it's very neat because you have essentially all the necessary information encapsulated in one page, which is good. So obviously you have the equations of each quadric we talked about. You have a description, the picture, of course, of the quadric and the description of the horizontal or vertical traces. Again, these are important pieces of information because it tells you what they are, but it's important to not just take them for granted. Just try to visualize that they are indeed the as mentioned, ellipses, hyperbolas, depending on the case. And even more important, remember, these are all for z-axis as the axis of symmetry, because you don't want to fill in the pages with lots of variations of the same formulas, right? So just to remember what I was talking about, if you look at the elliptic paraboloid, that's along the z-axis. But if I interchange y with z, so let's say I have y over c on the left and x and z on the right squared, that's going to be the same shape but along the y-axis. I think, did I say y? Anyway, so I mean, if you place y instead of z, that's going to be the same shape along the y-axis. I'll show you some examples with Maple in a minute. One interesting thing about, as a side note, for example, the hyperboloid of one sheet, one of the geometric properties of this object is that it can actually be generated by straight lines, which I think is rather cool. So I mean, if you pick a straight line that goes inclined, like tilted, like if you follow my mouse, you kind of see it, you know, and you rotate it around that narrow part, that narrow trace that is along the narrowest part of the hyperboloid, you can generate the entire hyperboloid with a straight line. That has some interesting practical applications. Let me show a bunch of pictures on the internet about this, right? So you can see here that if I rotate the red line, is going to be you're going to generate the entire hyperboloid, or even a more practical description, right? To actually see the beam. You have a beam that so basically you can generate the entire hyperboloid with a bunch of straight beams. So that has an interesting application because, first of all, a straight beam is a very simple shape to be produced, and you can generate a more complicated shape and even a round shape if you want by generating lots of these straight beams. In one of the applications of this property, for example, you can make gears, right, in the form of a hyperboloid, which could be a neat advantage if the transmission between the gears has to happen in some sort of an angle. I mean, like if you have some sort of space restrictions of some sort that requires you to have this angle transmission between two gears, and that's the hyperboloid will give you a solution of it. I mean, like a way out of the problem. Let's go over a couple of these examples with. We're going to go over an example of each with Maple. So first of all, the cylinder, right, which is given by a cross-section given by a parabola. Remember, because z doesn't appear in the equation, that means z can take any value. That's what creates the cylindrical shape. And obviously, if I change the meaning of the coordinates here, let's say I have y equals z squared, and I let x vary, that's going to be a cylinder along the x-axis, because now x can take any value. I'm not going to insist too much on the ellipsoid. It's pretty obvious. This is the more symmetric shape we talked about. I mean, all cross sections are ellipses. You clearly see that, horizontal or vertical. Let's take a look at the hyperboloid again. And let's visualize one of the cross sections here. So let's actually sketch a horizontal trace. Let's say at z equals 5. No, z equals 2, because it's not going to appear in the picture here. Z equals 2. So obviously it's going to look like an ellipse if you look it from above, right? The shape of the intersection. And a vertical trace is going to be a hyperbola. Let's say x equals 2. It's not going to be in the frame. So let's see, x equals 1, let's say. All right, so from the side, I'm sure there are better ways to sketch this, but I hope this is good enough, right? Again, if you follow the intersection from the side, it should look like a hyperbola, right? Let me make it actually at x equals maybe, let's do one along the y-axis. Let's say y equals 3. It's slightly better, I guess. So the two pieces of the hyperbola, right? The vertical trace. The hyperboloid with 2 sheets will have the same type of traces, but of course there is a gap here. So I mean, for example, if I sketch z equals 1, let's say. I mean, you can see the plane z equals 1, but obviously it's not going to intersect the hyperboloid, right? Because it's in that gap. But otherwise, the shapes of these traces will be the same as the one with 1 sheet. The cone, this makes sure you don't confuse it with the hyperboloid above because it has 0 on the right-hand side, right? So I mean, the equation of the hyperboloid with 1 sheet is very similar, except there's 1 on the right. The cone, on the other hand, it's kind of like a hyperboloid, but in which narrowest part reduces to 1 point. One of the consequences of this is that actually vertical traces again are hyperbolas, but except the one that goes exactly through the origin. The one that goes exactly through the origin, through like x equals 0, that's going to give you actually a pair of straight lines that intersect at the origin. That's one of the differences. Otherwise, from above, again, it's an ellipse, horizontal trace, vertical trace, a hyperbola. And then finally, the elliptic paraboloid, which again, I'm going to use it more often because this is the easiest, more general type of picture that you can use in Calculus 3, which is easy to sketch, easy to visualize. It's kind of like, I mean, if you know parabolas, you know paraboloids, you know, so the easiest quadric that is non-trivial, so to speak. So together with the ellipsoid, we're going to use that more often. Always remember, again, if I interchange, let's say I have x squared over, let's say x squared over 9 plus z squared over 4, let's say minus y. That's going to be, again, a paraboloid, but along which axis? You can pause and try to answer, but obviously it's going to be along the y-axis. Now, you always have to play around with the range because the viewing box may not be suggestive enough, right? So it's going to be along the y-axis, okay? If you really want to see it even better, I think we're going to have to extend x in the positive direction a little bit. There you go. Even more so, probably. Let's say 20. And I think I'm going to make it from 0. Well, still not good, actually. No. Let me see if I can. Sometimes it's not that easy to actually. I mean, it is possible. Yeah, I think that's good enough. Yeah. So I can see it better, you know, without any cuts, right? So paraboloid along the y-axis, open along the positive y-axis. Let's see. And then finally, the hyperbolic paraboloid, which like I said, sometimes this is confusing because it feels like there is a kind of like I mean, the confusing part is that you may think that the top here, this extends to the right-hand side, but actually it does, but also upward, right? I mean, it's really an infinite saddle. I think the better descriptions, I mean, because the viewing box cuts the surface above, right? But there are better pictures that you can look at on the internet and something like that. These are the better ones because they clearly tell you, I mean, show you how vertical traces are parabolas, either open down or open upward, depending on how you cut it above, you know, parallel to like a perpendicular to x-axis or perpendicular to the y-axis in this case. And by the way, this point, the low point of the saddle, has an important property that we're going to talk about when we deal with critical points of a function of two variables. It's actually called the saddle point, right? It's a point that is neither a maximum nor a minimum. The saddle is very suggestive for that property, right? I mean, it's either a low point or a high point, depending on the path of getting to that point, if you imagine yourself walking across the surface. Okay, so I think that's it for this section. I'll see you next time.